Hi everyone, this is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I will explain about definitions and terminology on fundamentals of design of machine elements. So in this, first we will discuss about what do you mean by stress and then strain and what is the relations between the stress and strain we will see. And more terminology also related to these fundamentals of design of machine elements I will explain. So first of all, coming to the definition of stress, when some external system of forces or loads acts on a body. So it means whenever the object is subjected to external forces or external load, the internal forces, those forces are equal and opposite, are induced at various sections of the body. So these forces are resistance to the external forces. So that these internal force for unit area at any section of the body is known as stress or unit stress. Suppose this is a cylindrical object subjected to a load P. Then this type of load is tensile load. So whenever the force is subjected, when this component is subjected to force or load, internal forces will be set F at various sections of the body. So generally the force lines are moving like this. So take a cross section. The cross section is like this. So this is a cylindrical object, so that you can write, you can draw. So cross section is circular. Suppose if it is rectangular, the cross section is a rectangle. So at this area, the internal resistance will be occurred. That that is known as unit stress or simply stress. So mathematically may be written as stress is equal to the Greek letter sigma load for area. What is the load acting? And what is the area, that particular cross section? The unit area at any section of the body. So you may take unit area, here also you can take, here also. So at area, at any area, any section of the body. So that area, suppose you have now taken example, cylindrical object. In cylindrical object, so diameter and length. The cylindrical object subjected to load. So how do you calculate the stress? Load is equal to stress is equal to load per area. So load upon area of the cross section, here cross section should be circular. So that area is 5 by 4 d square. Now substitute this area in this equation, you will get stress. So units are very important. What are the major units of a stress? In SI units, the stress is usually expressed in pascals. So the 1 Pascal is equal to 1 Newton per meter square. So again 1 megapascal is equal to 10 to the power of 6 Newton per meter square. 10 to the power of 6 Newton per meter square. Again convert into Newton per mm square. So divided with 6 Newton per mm square. So you will get 10 to the power 6, 10 to the power 6 get cancelled. You will get 1 Newton per meter square. So 1 Newton per mm square. So that 1 megapascal is equal to 1 Newton per mm square. Clear? So similarly, 1 gigapascal, 10 to the power of 9. 10 to the power of 9, 1 giga, 9 Newton per meter square. So convert into Newton per mm square here, 10 to the power of 9 divided by 10 to the power of 6 Newton per mm square. So get cancelled here, 10 cube Newton per mm square. So you can write in terms of kilonewton per mm square like this. Next, strain. What do you mean by strain? When a system of forces or loads act on a body, it undergoes some deformation. So whenever load is acting on a particular on a body, so some deformation will be occurred. This deformation may be lengthwise or diameter-wise. So this deformation for unit length is known as unit strain or simply strain. You can denote it by with letter eta is equal to, mathematically you can represent change in length by original length, delta L by L. Change in length by original length or change in diameter by original length, original diameter. So like this, you may be calculated strain. So again, these stresses and strains are classified into different types depending upon the type of load and then type of deformation. Suppose here shown in this diagram, this object is subjected to load, tensile load, equal and opposite force acting. So the stress will be induced in this object, tensile stress at this section. So sigma T is equal to P by L. Similarly, strain, change in length, delta L by L. So next term is Young's modulus or modulus of rigidity. You may be denoted with the letter E. Young's modulus or modulus of elasticity. This is relation between the stress and the strain with the help of Hooke's law. What do you mean by Hooke's law? Hooke's law is the stress is directly proportional to strain within the proportional limit. So you can write with the help of constant. So that is Young's modulus. Sigma is equal to E into eta. So E is equal to sigma by eta. So this is stress upon strain. And again, you can write, you may write Young's modulus E is equal to sigma stress by strain from Uppsala. Now again, you can substitute stress relation. Stress is equal to load per area, and strain is equal to change in length by original length. So that PL by and A delta L is equal to E. You also write like this also, PE is equal to PL by A into delta L. Delta L is equal to PL by AE. In terms of area and Young's modulus. Units are Newton for mm square. Next, other stresses are shear stresses. So, shear stress when a body is subjected to two equal and opposite forces acting tangentially across the resisting section. Then inside the body, the component shear stresses will be occurred. Due to the shear stress, shear strain will be induced. So here shown riveted joint example, the single riveted joint is one plate and another plate, plate 1 and plate 2. These two plates are joined with the alpha of rivet. So that these two rivets are separated by a force is called, this one is shear force. Two equal and opposite forces acting tangentially. So that due to this shear stress, the rivet may shear like this. The rivet shear after shearing. The diagram is you may draw like this. So due to this shear strain will be occurred. So deformation induced in the body. So another stresses also there, that the compressive stress. Compressive stress is also induced due to the compressive force. Same as tensile force stress. Units also same, Newton for meter square or mm square. Another important term is in fundamentals, Poisson's ratio. See, this Poisson ratio you may denote it by letter 1 by m. So it has been found, this Poisson's ratio experimentally, that when a body or component is subjected to load, it may be tensile load or a compressive load, within the elastic limit, then the lateral strain bears a constant ratio to the linear strain. So you may return mathematically lateral strain upon linear strain is equal to Poisson's ratio. So 1 by m or m is equal to lateral strain by linear strain. So linear lengthwise delta L by L, lateral delta D by D. So you may return the Poisson's ratio is nothing but it is the ratio of lateral strain to linear strain. When the body is stressed within the elastic limit. So already you know the elastic limit and professional limit, and then ultimate strength and yield point and fracture. Already you have learned in previous sessions stress strain relation that curve already drawn and studied. Next important term is factor of safety. So factor of safety is very important in design of machine elements. So you may write factor of safety FS or FOS. It is the ratio of maximum stress to the working stress or design stress. So the factor of safety is used in machine design of machine elements to avoid failures. This factor of safety is used for safe design only. So how do you take this factor of safety? Suppose we have maximum stress value, that is ultimate stress, upon the actual working or design stress. Actual working or design or permissible stress. Permissible stress. So then factor of safety will get. Example, suppose the ultimate stress is 250 megapascal. The working stress is, this is ultimate stress. That is sigma u. Working stress or design stress is 100 megapascal. So now calculate factor of safety. Factor of safety is equal to, so whatever maximum stress is there, so that is 250 upon 100. So here 2.5. So your factor of safety is 2.5. So by using this factor of safety, you may calculate other design parameters of a component. It means the component or object or a product withstand this maximum stress only or maximum load. But your applied load is 100. So beyond this the maximum load, if you are gradually increasing the load or stress, what will happen? The component will fail. So that is not safe. Suppose load is 1000 kilonewtons. So it means the component withstand up to 1000. But you can't use 1000 kilonewtons. So 900, 800, 700 only you can apply. Beyond this 1000, suppose you apply load, the component will fail. So that to avoid these type of failures, we need to calculate, need to take factor of safety. So that's why always the factor of safety value should be more than the 1 only, not less than 1. Clear? So next one is resilience. So resilience means whenever the body is loaded within the elastic limit, it changes its dimensions and on the removal of the load. So nothing but this in elasticity property. So after applying load within the elastic limit, some deformation will be occurred in the object. Suppose whenever you remove the load, so immediately it regains its original shape, original dimensions due to the elasticity property. So during this time, it has stored some energy in itself. In the body, within the body, some energy absorbed. So how much absorbed that energy stored is called as resilience. So that on removing the load, the energy stored in given off as in the case of a spring. For example, spring. So take one spring, apply load. So you remove load, so some elongation, so some delta L, so deflection will be occurred during application. So whenever you remove the load, so you can again regain its original shape. So which is absorbed in a body when strained, that energy is called as strain energy. How do you calculate this strain energy? So of with load and deflection. So much deflected. Next, proof resilience. The proof resilience for unit volume of a material is known as modulus of resilience. So this one also important property of a material. It gives capacity of the material to bear impact or shock. In previous models, previous resilience and strain energy, proof resilience for unit volume of a material is known as modulus of resilience. So that mathematically strain energy stored in a body, you may written like this: U is equal to sigma square into V by 2E. So load for U into half into W into delta. So sigma V sigma square V by 2E. Next, the modulus of resilience means, so already we have studied, for unit volume, the strain energy resilience for unit volume is called as modulus of resilience. Next, other stresses are the torsional shear stress due to the twisting moment or torque. So when a machine member is subjected to a action of two equal and opposite couples acting in a parallel plane, that is known as torque or twisting moment. then it is the mission member is said to be subjected to torsion. Due to this torsion, shear stresses will be occurred. This type of shear stresses are called as torsional shear stresses. Suppose cylindrical object, this shaft, one shaft is subjected to torsion. Length, L is the length of the shaft. So here due to this torque, twisting movement will be occurred. That is twisting movement angle. These are radius. So it is 0 at the centroidal axis. Which one? The torsional shear stress always at its center is 0. So maximum at the outer surface. At outer surface, maximum shear stress will be occurred. Shear maximum at a top surface. So the maximum torsional shear stress at the outer surface of the shaft may be determined by using the following equation. So this equation is known as torsional equation. Here T by J is equal to G theta by L, G theta or C theta by L is equal to 2 by R. In this, T is torque or twisting moment, J is polar moment of inertia, and G is torsional rigidity or modulus of rigidity, GRC. Theta is the angular twist, and length of the shaft or length of the object. Tau is the shear stress. What is the shear stress induced in the object due to this torque or twisting moment? R is the radius. Radius of the object cross section. So by using the previous equation, you may calculate torsional shear stress. So now another equation is there, that power transmitted by the shaft. So what is the equation? P is equal to 2 pi nt by 60. So here T is torque transmitted in Newton meter, and N is the rotational speed. So P is equal to 2 pi nt by 60. You may write T into omega. Omega is the angular speed in radians per second. So like this, you may calculate power. So by using this equation, you may determine torque also, 60p by 2 pi n. And then you can apply torsion equation. After that, you will get 5 by 16 in torque is equal to 5 by 16 into tau multiplied with the dq. So by using this relation, you may determine the shear stress. Next, bending stress in straight beams. The bending stress. So by using this bending equation, you may calculate bending moment and bending stress. The equation is m by I is equal to sigma by y is equal to E by R. Where m is bending moment and I is moment of inertia. And sigma is bending stress. And y is the distance of the cross section upper pi bar from its neutral axis. From its distance of outer surface. From its neutral axis. Similarly, E is the Young's modulus or modulus of elasticity. R is radius. So by using this bending equation, you may calculate the bending moment pi by 32 sigma b into d. So you may calculate section modulus I by y. See? And by using this equation, you may calculate bending stress. Bending stress is equal to m by I by y is equal to m by z. So that bending stress equation and torsional shear stress equations are very important for problem solving in design. Next one is theories of failures under static loading. So many theories are there. Theories of failures are there. So there are total 5 theories are there. So these theories of failures for a member subjected to biaxial stresses. Suppose, why should we use these theories of failures? Suppose a component is subjected to combined stresses, biaxial and triaxial stresses. In that kind of situation, we can't calculate the values, safe condition value or stresses values by using empirical relations. So that's why we will use the principal stresses and principal strains to avoid failure. So always these theories says use safe condition only to avoid failures. What is the condition for failure? What is the condition for safe design? So that's why these theories of failures we have to apply for our design of machine elements. So total 5 theories are there. First theory is maximum principal stress theory. It's also known as Rankine's theory. Second one is maximum shear stress theory, also known as Guest theory or Tresca theory. Third one is maximum principal or normal strain theory. Fourth one, maximum strain energy theory. also known as Higgs theory. The fifth one is maximum distortion energy theory, also known as Henke and von Mises theory. So now I will explain one by one. The maximum principal theory, according to the maximum principal stress theory, Rankine's theory, whenever the component is subjected to tensile load or normal stress, the failure occurs at a yielding point less than or equal to the what is the failure, what is the yield condition at in a simple tension test. The component is subjected to principal stress or normal stress. The failure occurs at a yield as compared to the at which yield occurs in a simple tensile test. That is standard test. It should be less than or equal to. So then only the design is safe. So here, according to this theory, you may write this maximum stress, principal stress or normal stress sigma 1 is equal to sigma yt by factor of safety under tensile stress, under a simple tension test. Here also the second theory, maximum shear stress theory, also known as Gestalt-Tresca theory, it says that the failure occurs due to shear stress when the yield begins, as in case of simpleton shear stress. So whatever obtained a value in a simple tensile test, that value should be more than the whatever obtained value by using this maximum shear stress. Similarly, the maximum principal stress, shear stress, here shear max is equal to shear yield by factor of safety. This is the condition. Third one, maximum principal strain theory. The strain occurred when subjected to maximum principal strain, normal strain. It should be less than or equal to strain occurred in a simple tension test. So whenever it is subjected to biaxial stresses, all theories are depends upon this biaxial stresses only. So biaxial stresses are sigma 1 and sigma 2. And shear stresses. Shear stress. So maximum strain energy theory, also known as X theory, the component fails at strain energy subjected to biaxial stresses. The strain energy should be less than or equal to whatever strain energy available from that simple tension test. Distortion energy theory also similarly maximum strain energy theory. But in this maximum distortion energy theory, we will calculate strain energy for unit volume. will consider here, will not consider here the strain energy theory will consider Poisson's ratio, but in this distortion energy we are not consider this Poisson's ratio. So this theory is very useful for mission components analysis, maximum distortion energy theory, for calculating the von Mises stresses. So whenever the object is subjected to biaxial stresses, so what are the deformation? At which deformation occurred? So what is the stress levels at the particular component? You may determine. So here, from strain energy theory, so you may write the equation, the shape condition, sigma 1 square, sigma 2 square, minus 2 sigma 1 sigma 2 upon by m is equal to sigma yt by m whole square. Similarly, in this distortion energy theory, same as strain energy, but only difference is there is no Poisson ratio. So biaxial stresses, whenever the component is subjected to biaxial stresses, the equation you may written like this. So this is this equation for safe condition, safe design. Next one is just the important definition is fatigue and endurance limit. So actually the fatigue property already you know, whenever the component or object is subjected to repeated loads or cyclic loads or repeated stresses or cyclic stresses, it fails at stresses below the yield point stress. Such type of failure, this type of phenomena is known as fatigue failure. So generally, in mechanical components, all mechanical components are, machine components are subjected to the cyclic loads. So actually, here I have taken the standard specimen. This specimen tested under fatigue testing mission. So what we have called as rotating beam tester subjected to bending. So what will happen? This is the upper fiber and the lower one. So the stresses vary whenever this object subjected to bending load starts to rotate in a fatigue testing mission. The stresses varies from compressive to tensile at upper portion, or upper fiber or upper portion. And similarly, at lower portion, the stress value varies from tensile to compressive. Tensile stress to compressive stress. So purely reversal bending. So after a certain number of cycles, this specimen will fail. So at which fails this object, at particular point you can calculate what is the fatigue strength of the component for the this specimen material, and corresponding number of cycles to failure also you may be noted. So all these values you can plot on a diagram. So that is called as SN diagram. Strength versus number of cycles to failure. Strength versus n. SN diagram. So I will show you now next slide. So the completely reversed stress. So compression to tension and tension to compression. This diagram is called stress time diagram. Stress time. So time plotted on x-axis and the stress values are plotted on y-axis. In this case, the mean stress is 0. So how do you calculate the mean stress? Sigma max plus sigma minimum by 2. The variable stress is sigma max minus sigma minimum by 2. So here one time compression and it varies from compression to tension and tension to compression. So that this mean stress value is 0. Sigma max and sigma minimum values shown in this diagram. So variable stress you may be calculate. In this diagram, in the C diagram, endurance limit or fatigue limit. Here shown stress versus number of cycles. So it is N and S. So that this diagram is called SN curve. SN curve or SN diagram. See the dotted line shown up to here, the component will not fail. Beyond this dotted line, the component will fail due to the repeated stresses. This limit at which the component fails, so we stand up to the after a number of cycles. So here, see, suppose this one is standard number of cycles are 7, 10 to the power of 7. Up to here, 10 to the power of 7, the component will stand. The component will not fail. At this number of cycles, the stress is endurance strength. Endurance limit or endurance strength. This endurance limit or endurance strength value depends upon the component material and the type of loading. So that's why we will take load correction factors while solving problems. Next, coming to this repeated stress diagram. The stress versus time. So here the minimum to maximum and the maximum to minimum stress vary. So that in this repeated stress, there is a mean stress sigma max plus sigma min by 2. So here minimum 0, the maximum value you can calculate. And variable stress also you may be determined by using this relation sigma max minus sigma min. Next, fluctuating stresses. The stresses fluctuates. So mean stress you may calculate, and variable stress and sigma max and sigma min. So for fluctuating stresses, the diagram shown in this slide, you have to draw like this. Mean to maximum. So next, effect of loading on endurance limit. What is the effect of loading on endurance limit? Sigma E. So generally, the stress SM curve plotted by using the experimental values under rotating beam testing method. Whatever values obtained, those values plotted on this diagram. But sometimes mechanical machine members are subjected to other loading also. So in that case, the endurance limit may be vary. That is depends upon the type of loading. One is bending load, bending loads, and another one is axial loads, and shear loads. So you should take under bending loads, bending load correction factor, axial load correction factor, and shear load correction factor. So you should multiply this factor with the standard endurance limit stress value, whatever you got from experimentally. So then only you will get the actual endurance limit for bending loads. Suppose take first case for bending loads. For bending loads, sigma EB, endurance limit under bending load, sigma E, sigma B multiply with sigma B multiply with sigma E multiply with KB, you will get bending load endurance limit. So always take the KB value as unit, one value. So you may be assume unity. KB value is 1 per bending load. Similarly, other axial loads also you may calculate. For axial loads, so take the load correction factor is Ka. How do you calculate? Sigma Ea is equal to sigma E multiply with Ka. So here you may take the Ka value 0.8. Similarly, for shear loads, sigma tau E shear loads Es is equal to tau E into Ks. Ks is here. K is the axial load correction factor and Ks is the shear load factor. So you will get endurance limit values for different loads. So other factors also there. So I'll explain here. Other factors are surface finish factor. surface finish factor. Suppose here other factor surface finish factor. So that is K surf. The component is subjected to bending load and considering surface finish factor. So in this case, the sigma E1 is equal to sigma EB multiplied with K surface finish factor. So already we have calculated in the previous step, sigma EB is sigma E multiplied with KB multiplied with K surf. So that sigma E is KB is equal to 1 and K surf you may take 0.55. So you will get surface finish factor for bending loads while considering surface finish factor. So similarly, other factors also there, size factor equation. So how do you write the size factor? So when considering size factor, so how to write the equation for endurance limit? Size factor, K size. For bending load, sigma E dash is equal to sigma E1 multiply with K size. Size factor, sigma E1 is sigma EB into K surface multiply with K size factor. The EB, sigma E, KB, K surface and K size. So this is a new endurance limit value for the component is subjected to bending loads. When considering surface finish factor and size factor. The other miscellaneous factors are also there, reliability factor and K temperature factor KT and impact factor Ka. So whatever available given factors, you should multiply with sigma E. So like this, how to write the equations for endurance limit. What is this is the effect of endurance limit on loads, different loads. You should use load correction factors. Next one is stress concentration. So very important term or important phenomena in design of machine elements. So what do you mean by stress concentration? Suppose whenever an object is subjected to some tensile load or compressive load and it carries forces from one end to another end uniformly. So assume as a uniform cross section. There is no disturbances and uniform stress distribution is possible in that uniform bar section. In that case, there is no stress concentration. So first of all, what do you mean by stress concentration? Wherever the holes or notches or pockets are available, it means whenever the object changes its cross section suddenly, there more stress will be occurred. This phenomenon is called as stress concentration. When compared to the surroundings this compared to the surroundings, wherever these walls and notches are present, in that region more stress concentration will be possible. I will explain. Take one example here. This component is subjected to tensile load. This uniform work so that the force lines are uniformly distributed. These lines are called as force carrying lines. This is a uniform bar. The stress distribution is uniform in this uniform bar section. So you take any section, here also same, and here same force, same stress distribution is possible. So that in this case, you can calculate the stress value by using elementary equations. The elementary equations are the tensile stress is load per area, and the compressive force by area, and shear load by area. So like this you may be calculated for this uniform bar section. Suppose the cross section is like this. So here up to here uniform. Suppose this component also subjected to load, tensile load. So in this, the load carrying lines are up to here, they are in uniform. But here suddenly changes its direction. So it means at this region, more stress will be concentrated. This phenomenon is called as stress concentration. So how to avoid this stress concentration? We will see in next session. So we should take stress concentration factors. And in this case, see up to here, uniform cross section, so you may calculate the stress values by using these elementary equations. But at this region, how do you calculate stress? In this, two types of stresses are there. One is normal stress, another one is localized stresses. So at which the cross section changes its shape or dimension, their localized stresses are induced. Their stress concentration will be present. So how do you calculate? So that we need to calculate theoretical stress concentration factor. So the theoretical stress concentration factor is ratio of localized stresses to normal stresses. So you will get one factor. You should multiply this factor with the endurance limit. And how do you reduce? How do you reduce the stress concentration? By using, by creating words, deleted words, extra words, by creating notches, by creating fillets. Always to avoid sharp corners. Wherever the sharp corners or edges are present in the object, there must be stress concentration. Stress concentration is possible. So, example: suppose in this cross section, the previously object is like this. So the stress distribution lines are like this. To avoid, so here more stress concentration will be present. To avoid stress concentration, what you have to do here? Create fillets. So due to these fillets, smooth flow lines will be possible. So in this region, when compared to the previous one, somewhat stress concentration will be reduced. So that in machine components, you can't eliminate permanently the stress concentration, but somewhat you can reduce by using different methods. So what are the different methods and how do you calculate this theoretical stress concentration, and what is the relation between the fatigue stress concentration factor when subjected to fatigue loads? What is the relation between this fatigue loading, fatigue testing, fatigue test, stress concentration factor and the theoretical stress concentration factor? I will explain in next sessions. Okay. So these are the references I have taken. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.